Yes, please.
Very good. Well, welcome everybody to today's Vamos seminar. And before we get started, I want to welcome Tom Weinach, who is joined the Vamos board. We are looking for increased representation across various areas in AMO physics. And so we're happy to have Tom as part of the board. So today I'm really delighted. This is the second in our series of the postdoc doubleheader. We very much think it's important to hear the voices of the young and up and coming in our field, and we have two of those wonderful young up and coming physicists. So I will begin introducing our first speaker, who is Zak Burkley. Zak got his PhD from Colorado State, working with Dylan Yost, and there he was working on developing high power deep UV lasers for novel experiments on hydrogen. Because such lasers would also be useful for spectroscopy in muonium, it was natural for Zak to move to Switzerland, and he went there to apply his skills to push the forefront of muonium spectroscopy. At ETH, Zak also became interested in studying quantum gravitational states of atoms, and they have a new seed grant there, and he and his family are enjoying Switzerland and hopefully will enjoy the seminar to come. So Zak, take it away.
All right, thank you, Ivan. And thank you, Vamos organizers, for creating this virtual platform to share exciting and interesting AMO research during these very unique times. Today, I'll be talking to you about exciting exotic atoms. And the exotic atom that we're exciting is muonium. So I'll be talking about precision spectroscopy muonium that's being done at ETH Zurich and the Paul Scherrer Institute. So what is an exotic atom? Well, let's compare it to ordinary atoms. For an ordinary atom, we have a positive nucleus and negative electrons. Simplest ordinary atom, hydrogen. For exotic atoms, there's many ways you can make them. One way is you can replace the electron with a negative particle. For example, with hydrogen, you could replace the electron with a muon, and you get muonic hydrogen. And already, this example is a great reason why it's so interesting to study exotic atoms. Because the muon is much heavier than the electron, it sits much closer to the proton, and therefore it's very sensitive to these finite size effects. And we were able to measure the proton radius very precisely doing spectroscopy of muonic hydrogen about 10 years ago. And what's very interesting is that they saw that this value was off from the average value of hydrogen spectroscopy. And this created what was called the proton radius puzzle and motivated a lot of new measurements in hydrogen. Other exotic atoms where you replace the electron with a negative particle, you have pionic helium, you could have anti-protonic helium, or we could replace the nucleus with a positive particle. In that case, you could replace the nucleus with a positron, and you have positronium. You could replace the nucleus with an anti-muon, and you have muonium, an anti-pion, pionium, or you could replace both, and we get anti-hydrogen. I'd like to point out that there's been a lot of just exciting research this year alone on exotic atoms. We see here that we had the first spectroscopy of pionic helium occurred earlier this year. With positronium, there were some nice measurements this year on the positronium negative ion, as well as a microwave measurement of the positronium fine structure. And what's really interesting about this result is that the measurement was several standard deviations away from the theoretical value. And this is an open-ended question that is yet to be resolved. So this should motivate more measurements on positronium. And what I'll be talking to you about today is muonium. And there's been some nice advances in control of muon beams that will greatly help the ability to make muonium in the future. And one of the articles that our group contributed to was creating a metastable beam of muonium. And as well, this year alone was another nice measurement on one of the transitions in anti-hydrogen, measuring some of the fine structure. So today I'm talking about muonium spectroscopy. So we'll start with some quick facts about muonium. It was discovered in 1960, and this was about 30 years after the discovery of the muon. And how they discovered it is that you can form muonium by electron capture. You can shoot it through gases, through thin foils, or onto silica targets. It'll capture an electron, and muonium should diffuse out. But how do you distinguish muonium from muons? Well, the lifetime of a muon is about 2 microseconds, and its primary decay channel is a muon to a positron and 2 neutrinos. So as we see here on the picture on the right, if you put a muon in a magnetic field, denoted by these X's, and you have a positron detector on the left, since the muon, when it decays, the positron is emitted preferentially in the direction of the muon spin. As this muon processes in this magnetic field, we'll see these jumps in positron detections on this positron detector. Now, muonium with the electron has a gyromagnetic ratio about 100 times larger than the muon. So then it will process about 100 times faster. And so this was the signature they looked for when they discovered muonium. Some other interesting facts about muonium: it doesn't actually follow the onium convention. This is generally reserved for a particle and its antiparticle, such as positronium. And in fact, there's research on what's called true muonium, a muon and an anti-muon, but today I'll be talking just about muonium, which is an anti-muon and an electron. Other facts about muonium: it's a very QWERTY efficient atom. You can type it with your right hand only. And other ones you can type with your right hand include pionium, this other word I didn't make up, monomolybdenum, and lollipop. And here's a picture of my son who is very happy to demonstrate this last word. But maybe a little bit more interesting to physics than the ability to type it with your right hand only is that muonium is a purely leptonic system. So why study muonium? As we saw with muonic hydrogen, it was able to amplify these finite size effects from sitting so close to this proton radius. It's very sensitive to it, and that made it such an interesting atom to study. Muonium's on the other end of the spectrum. Being a purely leptonic system, it's free from these finite size effects. And therefore, through precision measurements, it can serve as a very good test bench of bound state QED. And you can determine fundamental constants very well, such as the muon mass. And the Rydberg constant can be determined independent of the proton radius, which is very interesting. And it can help search for new and unresolved physics, such as effects of gravity on antimatter, lepton flavor violation. Very interesting is a lepton universality test. Can look for dark forces. And also interesting is the muon G-2 measurement, which if they reach the precision that they're hoping for in their future measurements, the comparison between theory and experiment will eventually be limited by the knowledge of the muon mass or magnetic moment of the muon. So today I'm talking about Muonium Spectroscopy at the Paul Scherrer Institute in Switzerland, shown here in the center. It's a wonderful particle accelerator facility that I have the privilege to work at here, and it's about an hour outside of Zurich, Switzerland. And the two measurements I'll talk to you today about are the mu mass measurement, where we'll be measuring the 1s-2s transition in muonium, and the Lamb shift measurement, where we'll measure the Lamb shift in muonium. And the goals and impact of these measurements is we hope to obtain the 1s-2s transition frequency in muonium to 10 kilohertz, get the best determination of the muon mass at a level of 1 part per billion. And through the 1s-2s measurement, you can get this muon mass fairly independent of assuming that QED is correct. It will give a test of charge equality between the first two generations of leptons with a very high sensitivity as well. And the goals of MuLam is to get the transition frequency to 100 kilohertz and be able to test QED corrections at levels comparable to the muonium hyperfine structure measurements. So the best measurement that's been done on muonium was a 1s-2s pulse spectroscopy. The best measurement on the 1s-2s transition was in 1999, and it was a pulse measurement. And they had about 10 megahertz uncertainty and a 20 megahertz line width. But if we look over at this transition, this 2-photon transition has a natural line width of 144 kilohertz, limited by the muon lifetime. So this 20 megahertz line width is leaves a lot to be improved. And the main limitations of this measurement were the use of a pulse laser that brought in this line width and introduced these large megahertz systematic effects. Now, the goal of MuMass is to do the first Muonium 1s2s CW spectroscopy. So in this weak excitation regime, the excitation rate is proportional to the number of muonium atoms, the intensity squared of the laser, and the time squared. So if we can get a high yield of low energy muonium, then we can decrease these requirements of laser intensity. And we can start having the conversation, is it possible to do this measurement without the need of a pulse laser? And as I'd like to show you, what we've developed for this MuMass measurements is that we indeed have a high yield of low energy muonium at 100 Kelvin, and we have high power 244 nanometer light, and that is a CW laser. And this will get us to the point where we can do this first CW spectroscopy. So how this experiment will look is that we'll have a muon beam here in the 1. It will hit a carbon foil, which I'll talk about the importance of that later. Then it will go onto a silica target that's on a cryostat. And here, the muons will capture an electron and diffuse out at the cryostat temperatures of around 100 Kelvin into muonium. The muonium will then pass through this high power 244 nanometer laser that is built up in a vacuum cavity, and it will go to the 2s state. This metastable state will be quenched with quenching electrodes, and we will detect the subsequent Lyman alpha light with a Lyman alpha MCP. And finally, when the muonium decays due to the muon decay, we will look for the positrons with some positron detectors. So the requirements for the CW spectroscopy that I'm showing here on the right are 1, a high yield of low energy muonium. So what's important there is this muon beam coming in this cold finger. As well, requirement number 2, this high power CW laser at 244 nanometers. And number 3, what's important because it is an exotic atom, meaning we don't have a large amount of it. We really need background suppression and good Lyman alpha detection. And I'll talk about at the end of the talk today how building this requirement at number 3, we actually realized we have the tools to do a muonium lamb shift while we are building everything for this 1s2s measurement. So requirement number 1, low energy muonium that comes out at cold temperatures. How this is created is we take the proton cyclotron at PSI, and there's some pions that come from this, and we can get a surface muon beam from these pions. And then this goes into a noble gas moderator. And here we can get low energy muon beam tunable between 0 and 30 keV. It comes down a beamline into this red interaction region. And this is where I would like to focus for today. And in this interaction region, as we talked about, we'll have this cryogenic target. We will have our high power 244 nanometer laser and our Lyman alpha detectors and quenching electrodes. And what I'd like to show you here on the top right is this is work that has been done in the past at this limb beamline, that for 5 or 6 keV incoming muons hitting this 100 Kelvin cryogenic target, the conversion to muonium is 20%. And this is very good. And this is into vacuum. And this is our check mark number 1. We have this low energy muonium at high yields, which is important for the CW spectroscopy. And here's a picture of the end of the limb beamline where we plan to do these measurements. Here's a CAD model. We'll bring in a 244 nanometer laser system that we're building at ETH. And we'll have a vacuum cavity that is integrated inside of the end of the limb beamline. And we're actually assembling this all now and plan to bring it up to PSI in the next 2 weeks. And I'd like to talk to you now about requirement number 2, this high power laser at 244 nanometers. How this laser operates is it starts in the infrared with an extended cavity diode laser at 976 nanometers. It's then amplified twice through a tapered amplifier and a ytterbium fiber amplifier. And this ytterbium fiber amplifier is very key as it gives us a high amount of 976 such that we can generate a lot of power in these doubling cavities. We go to 488 and then we go to 244. And thanks to some significant advances in the generation of this high power UV light, we are able to get up to 1.5 watts of power at 244 nanometers. And this picture on the right is a picture of our green cavity here before we put in this nonlinear crystal for doubling. Well, 1.5 watts is great. It's much higher than what's really commercially available. It's still not enough. If you remember, this rate was proportional to the intensity squared of the laser. And we still need about an order of magnitude or more power, because that will increase the signal by a factor of 100 to 1,000. So what we need to do is we need to enhance this 244 nanometer power in a vacuum cavity and have it stable for long times, because we'll be running this at a facility. We have beam time only a couple of weeks a year. And of course, everything needs to run perfectly for those 2 weeks. So here I have a picture of our intercavity UV power, and we have this in some oxygen. And this is at 20 watts, and we see it stable for about an hour. Being in oxygen, this requires some differential pumping, which we are able to implement by restricting the cavity to this 3mm aperture all the way through the vacuum system. And inside the center part is our spectroscopy chamber. Now, while this is very stable, what actually degrades over time is the optics leading up to the vacuum cavity, even though there's less power on these and they're not in vacuum. So what I have here a plot of is our UV power after our CLBO crystal. We have 1 watt stable for several hours. Then we have to go through some isolation optics before we go into our linear cavity. We take a big hit in our power. You work so hard to make it, and through every optic, you lose a lot. It's a little bit sad, but that's life in the UV laser game. And then after some lenses, we take another hit, and we see the rate starts to degrade at around this 4 or 5 hour time scale. And we can take a look at pretty much all the optics leading up to the vacuum enhancement cavity have this damage on the coating. I do not believe it's photocontamination. I'm unable to scrub it off or get it off with any cleaning method. And I really think the coating's just been stripped here. However, things look very promising. We were able to generate the M mode in our cavity clearly for Muonium. And it provides some really nice pictures, and it's wonderful to work with. And with that, I'd like to take maybe 1 or 2 minutes for any questions that people have so far.
Zach, I think with the timing, we're going to just take all the questions at the end. So,
okay, thanks,
yep.
Evan. So, as I talked about earlier, on the way of building our 1S, 2S technology, we realized we can also do the lamp shift measurement, because with an expected rate of 10 to 100 muonium in the 2S state per hour, it was very critical for us to suppress our background and test the Lyman alpha efficiency. So for the MuMass experiment, what we need to count as a signal is we need to trigger that we have a muon coming through our carbon foil. So here's our signal number 1, that we have a muon. And when we get this trigger, it says, hey, you should look a microsecond or 2 later for any metastable muonium. You should be looking for Lyman alpha light. And then 2, we see this Lyman alpha light. And then 3, we see the decay of the muon through a detection of a positron. And that's our triple coincidence to eliminate any background and be sure that we saw an event. However, we realized if, like hydrogen, then at low muon energies, this beam foil technique of sending a muon beam through a thin carbon foil, it could give high muonium conversion and actually a sizable amount in the metastable 2S state. And since we already have quenching electrodes and Lyman alpha detectors for measuring atoms in the 2S state, we could imagine, well, then we can actually do a muonium lamp shift measurement as well. And this is very overdue for a new measurement. The last measurement was 30 years ago with an uncertainty here, much, much larger than what is now theory is at. So how we plan to do the lamp shift measurement is we'll take the muon beam line from PSI, where we have about 10,000 muons per second. They'll hit this carbon foil, and we can get, I'll show you the results here that show this, about 200 muoniums in the 2S state per second. And then to do the lamp shift measurement, what we're going to do is we're going to depopulate the 2S state by mixing it with the 2P state, and we'll look for this, this lack of 2S atoms, meaning that we successfully drove the transition from the 2S to 2P. So what we first do is we'll send it through a hyperfine selection stage, and then we'll go and we'll through a resonance stage to do the hyperfine transitions that we would like. And then we'll go through our quenching region and Lyman alpha detectors that we're building for the 1S, 2S. And then instead of having to look for positrons, we can just have the muonium that's left hit a back detector, and this is our stop signal. So again, we'll have this triple coincidence for the lamp shift measurement. And last year, we had a couple-day beam time at PSI to test our detectors and our tagging method. And what we did is we had the carbon foil, our tagging MCP, that when the muons knocked off these secondary electrons. And then we have our quenching field and our Lyman alpha detectors. And then we have a rejection electrode at the end. So when the electrode's on, only muonium makes it to our back detector. When it's off, muons and muonium. So what we were able to determine was, one, the amount of muonium that is converted as the muons go through this carbon foil is a function of the incoming muon energy. And then two, with the quenching field and Lyman alpha detector, how much of that muonium was in the metastable state. And so I'd like to show those results now. Here is a plot of one of our measurements with the rejection electrode on in the orange and the rejection electrode off in the blue. And this is how we could determine the muonium fraction for different muon incoming muon energies. And we see here it decreases at lower energies, but thanks to the low energy muon beam line, we're able to get down to 4 or 5 keV muon beam. And there we're getting almost 50% conversion efficiency to muonium. And then we wanted to measure how much of this was in the 2s state. So this picture on the bottom left, this graph is the quenching on and the quenching off. So with the quenching on, we should look for Lyman alpha counts. Here in the orange, we see them. And with quenching off, we shouldn't see any Lyman alpha. And indeed, we didn't see any definite signals of Lyman alpha in this specific time window. And after taking into consideration all of our detector efficiencies, we were able to estimate that we're actually producing about 100 muoniums per second in the 2s state. This is 3 orders of magnitude better than what has been used in the past for muonium lamp shift measurements. So we're very excited to try this lamp shift measurement here in 2 weeks and hope to see some really good statistics. With that, I'd like to conclude that we're actively working on the mu mass measurement here, the 1s, 2s, and in a couple of weeks, we're going to try this first CW excitation of the 1s, 2s transition in muonium. And the long-term goal of this measurement is to measure this transition with a 3 orders of magnitude improved accuracy and get this muon mass at 1 part per billion. And this is possible with advances that we've shown in these high-power deep UV lasers, low-energy muon source development, and extraction of this cold muonium to vacuum. And as well, along the way, we'd like to improve the muonium lamp shift measurement. And this is kind of low-hanging fruit thanks to the advances in muon beam and muonium production, and goes along very well with our methods to detect for our mu mass detection. And kind of the future of muonium spectroscopy at PSI is they're developing this mu-cool system that will give it'll give an increase in a couple orders of magnitude of low energy muons, which would be a real game changer in terms of statistics. With that, I'd like to acknowledge my MUMass team and PSI collaborators, the ETH Institute of Particle Physics and Astrophysics, Jesse Zhang, a student that helped develop the laser with me, the Colorado State group of Dylan Yost, the PI, Paulo Crivelli, and the VAMOS organizers. And of course, none of this would be possible wasn't for my family that moved over with me to Switzerland, and very thankful for them for doing such a big move. And I'd like to thank you all for listening, and happy to take any questions.
Thanks very much, Zach. So one thing I failed to say at the beginning, if you want to ask questions, please enter them into the Q&A on the Zoom and equivalent if you're on the YouTube. We do have some questions, so I will start asking them, but if you have other questions, please enter them and we'll try to get to them. The first question is from Christoph Pachuki, who asks, what is the time scale for the 1S to 2S measurement?
Right, so we have 2 phases to this measurement, and in the first phase is over the next 3 years, and we hope to get down to 100 kilohertz, 50 kilohertz uncertainty in this time. And the line width we hope to get in these first phase is a 700 kilohertz line width. And I have some actually plots, graphs here that maybe will help kind of our goals here. So yeah, 750 kilohertz and less than 100 kilohertz in our phase 1. And then after phase 1, so 3 years from now, we hopefully will start phase 2, where we'll aim for getting down to 300 kilohertz line width and 10 kilohertz statistical uncertainty. So the MUMass collaboration really just started last year. And so over the next 5 to 6 years, we hope to reach these goals.
There's a slightly clarifying question here from Christoph. He says he means for 10 kilohertz.
Yes, for the 10 kilohertz, this will take place in our phase 2 measurement, and we hope to start the phase 2's measurement in 3 years. But that'll be a couple of years of having a few weeks of beam time. So really, this phase 2 10 kilohertz, we hope 5-year time span to get to that level.
Okay, very good. Next question comes from Bima Butker, who says, thanks for a great talk. And the question is, presumably oxygen is used to preserve those UV mirrors. Is it now understood how this works?
Yeah, it's a great question. And so I have some experience with this through my time in Colorado and here at ETH. Originally, these enhancement cavities that we built, we used silicon mirrors with a few silicon mirrors with a silicon oxide coating. And we saw with these oxide coated mirrors, they required 1 torr of oxygen to prevent severe degradation. If you went below this 1 torr of oxygen, there would be contamination on the mirrors in vacuum. You could remove it and scrub it off and put them back in. And this degradation mechanism is possibly due to surface oxygen depletion, which is helpful for having the oxygen in there, or hydrocarbon contamination, which can also be avoided if you have the oxygen in there. The oxygen with the interacting with the UV actually is somewhat of a cleaning mechanism. So at ETH, what we're trying though is we are trying some fluoride coatings. So if we have a calcium fluoride coating on a fluoride substrate, hopefully we can remove the surface oxygen depletion. And what we've seen so far with these fluoride coatings is that the buildup is a little bit lower than the fused silica, but they're very consistent behavior. And I don't see any signs of severe degradation or photocontamination when I go to high vacuum. And I think we've seen maybe 5 to 10 watts of intercavity vacuum power at high vacuum with these calcium fluoride mirrors over a couple hour time scale, and we don't think they're degrading. As you've seen, actually, the thing that's degrading are these optics outside of vacuum leading up to the cavity.
Very good. All right, we have a couple of questions from our panelists. Tom Weinach asked, what is the 2-photon Rabi frequency that you achieve with the maximum UV power? And also, what about AC Stark shift? Do you know what these are for your maximum power?
So for the Rabi frequency, what we choose is this value from this 2-photon paper by Haas et al. And I believe for a 2-photon transition, it's 8 pi times 3.68 times 10 to the minus 5 watts per meter squared. And then hertz in there is the Rabi frequency that we use when we're on resonance. Well, just the Rabi frequency, yeah. And the AC Stark shift at the end, as we see here, I think the main systematic will really be from the second order Doppler shift versus the AC Stark shift for these measurements.
Terrific. Okay. I think
the great news is about the UV, the things degrading over time is really, we're just baking that in. So we already have built in how to do an AC Stark shift extrapolation. Our optics will degrade and the power will just go down, and we take care of both things right there.
Terrific. All right. I think we will stop there. And thank you very much again, Zak, for a super talk. Really interesting. Thanks.
Thank you, everyone.
All right. And next up, we are very happy to welcome and introduce Alejandra Collopy, who from NIST in Boulder. Alejandra did her undergraduate at Stanford as a physics major, and then did her PhD at CU Boulder under the supervision of Junier, where the subject of her dissertation was implementing magneto-optical traps for neutral yttrium oxide molecules. After completing her PhD, she gets moved across the street to NIST Boulder, where she's doing her postdoc, working on this, doing spectroscopy of molecular ions, and that's what she's going to tell us about today. So welcome, Alejandra. Again, if you have questions, everyone, in the Q&A chat box on Zoom or equivalent on YouTube.
All right, thank you so much for that introduction. And thank you to the organizers for putting all this together. It's nice to have a little bit of togetherness, even though we're all so far apart. So I'm excited to talk with you today about some of the work that we're doing in the NIST ion storage group, in particular, our work with the molecular ions and trying to improve our control over them. As you can see, a great number of people have been involved in this work. And our labs are at NIST, but a number of these people do have CU Boulder affiliations. Oh, sorry. So just a brief motivation about why we want to look into molecules in general. Molecules can be great tools for precision measurement. They can have near degenerate states, which enhances their sensitivities to external perturbations. And so they make really good test beds for searches for beyond the standard model physics. You can also use molecules to study cold chemistry and study the interactions between the molecules and even gain quantum control over chemical reactions. And another exciting frontier is looking to use molecules for quantum simulation. They have tunable, long-range anisotropic interactions and a rich internal structure, which we'll see as both a feature and a bug. As I said, molecules contain many different energy levels. Just like atoms, they can have electronic transitions that are at the hundreds of terahertz scale, but they can also vibrate at a lower energy scale, and even lower than that, they can rotate. And we even have energy scales in the gigahertz, megahertz, and kilohertz range for molecules. So a single molecule can have many different energies all within the same molecule. And this richness of structure is great, but it also means that it can be a little bit harder to manage and control the molecules. So if we're going to step back a bit and write a wish list of things we want in order to control our molecules, we'd really like to be able to hold on to them for a long time so we can probe them repeatedly and interrogate them for a long time. We'd like to have good state detection so that we know what state that we're in. And we'd really like the state detection to be non-destructive so we don't have to reload every time we want to reinitialize our experiment. We want to have good state preparation, so we want to be able to get our molecule to the state that we want to study. And then once it's there, we want to be able to coherently manipulate the molecule. And maybe if we get lucky, we can go shopping and find remote control for this, but we might have to develop our own techniques. I am going to only be talking about molecular ions in this talk. A lot of work is going into control of cold neutral molecules, and Conquan gave a really nice talk last week if you want to hear a little bit more about that. So our ions are trapped in what's called a Paul trap, and it's a pretty simple thing. We have 4 electrodes. 2 DC segmented electrodes allow us to get axial confinement. And we can't make an electrostatic trap for charged particles in 3D, but what we can do is by applying RF time varying potential to our 2 RF electrodes. So here we're looking end on along the axis. We can create a pseudo potential that provides confinement for the ions. On the right here, we have a picture of, it's actually the twin sister of the trap that's in our chamber. But you can see that there's an RF electrode and DC electrodes coming in. And we have another wafer on the other side, so we get all 4. And for a sense of scale, this electrode is about 4 millimeters long. So ion traps are great. They can give you a high trap depth and long trap lifetimes. And so we can readily take care of the trapping for it. Here are some pictures of trapped ions from our own group. This one on the left is actually a different kind of trap called a penning trap, but allows you to trap a large 2D crystal array. Or you could trap a chain of ions. And over here, you can see the ions in our experiment. We've got a calcium ion that's bright and a dark calcium hydride molecular ion that I promise you is there. There's a lot of different molecular ion techniques out there. This is a non-exhaustive list, and I'm sorry if I don't have your favorite on here. There's some detection methods that are very powerful but are destructive, such as photodissociation. or oriented photofragmentation. And others can be non-destructive, but might be difficult to adapt to detecting a variety of states, such as state-dependent optical dipole force. The technique I'm going to be talking to you about with you today is quantum logic spectroscopy, and I hope to convince you that it could be a really versatile tool for looking at a lot of different systems. So I hope I've motivated our problem a little bit to you. I'm going to talk with you about what quantum logic spectroscopy is and how we implement it in our own system, and then how we use it to perform rotational spectroscopy for our calcium hydride molecules. Just gonna have a very brief interlude to tell you about how we can also use this as a tool to make entanglement between states in the atom and the molecule. And then I'll finish up by talking with you about a systematic we've been investigating lately. So what is quantum logic spectroscopy? The long and the short of it is that we put a difficult ion in a trap that we want to study, along with a well-behaved logic ion that we can control and understand very nicely. So in our case, we co-trap a calcium hydride ion with a calcium ion, and the calcium ion is going to do all of our heavy lifting for us. And this is actually the same way that the aluminum ion clocks work. In our group, we have traps where an aluminum ion is co-trapped with magnesium or calcium, because we want to study a very narrow transition in aluminum, but direct cooling and detection of aluminum would be, we don't have the lasers there for that, but hopefully someday. So the important thing is when we have two ions trapped in the same motional well, because of the Coulomb interaction between the ions, they have a shared motional state. And we're able to use that shared motional state as an information bus to transfer information from our spectroscopy or difficult ion to our logic ion. And really importantly, when we read out this motional state via the logic ion, it's non-destructive to the internal state of the molecular ion. So once we've read out the information, we know what state the molecule's in, and we can go and perform further operations on it. I'm going to walk you through just briefly how this works in a system. So we have to initialize in the ground state of the motion of the two ions, but we can do this with cooling the calcium ion, which also sympathetically cools the motion of the calcium hydride ion. I have here two states labeled up and down for calcium, two states up and down for calcium hydride, and then they have this shared motion in between. So what we can do is we can attempt to drive a transition that will change the molecular state, but will also add a quantum motion to the shared motion. And then after we do that, we can attempt to drive a transition on the calcium ion, which not only changes the state of the calcium ion, but takes that motion away. And we are really capable of detecting whether we made this change in the calcium state. And so we know that if we were able to drive this transition, then we were able to drive this transition in the molecule. In addition, what's important is if this transition frequency in the molecule that we're attempting to drive is unique within the molecule, then the molecule has been projectively prepared in a pure quantum state. And if we want to be very, very sure, we can repeat this process many times to increase our certainty that we are in the state that we want to be. So here's an overview of what our particular system looks like. We have a linear Paul trap over here where we trap our calcium and calcium hydride. We have a number of laser beams addressed in the calcium ion in order to provide the cooling and the state detection. And we have two different lasers that we use to interact with the molecular ion. We have a 1051 CW fiber laser that we can use to drive transitions that are within a rotational manifold. And we have a frequency comb that we use to drive transitions between rotational manifolds. And because this frequency comb is a pulse laser, we do have a delay stage to ensure that the pulses arrive at the ion at the same time. I want to make clear here that these two lasers are driving stimulated Raman transitions and have a very large attuning with respect to any molecular transitions. And so they should be easily adaptable to different molecular species. We've sort of tested this in reverse. This laser recently died, and after a brief funeral for it, we swapped it out for a 1064 nanometer fiber laser, and we were still able to drive the transitions in the molecular ion as we expected. And a little technical detail, we set these laser beam powers in order to cancel differential AC Stark shifts on the molecule. So one of the nice things about relying on stimulated Raman transitions, not only does it mean we can use very far detuned lasers, but it also means that since we only have stimulated emission, we prevent leakage in undesired states. We don't have to worry about falling into different rotational vibrational levels than the ones we're trying to access. And we have the frequency resolution for these to drive sideband transitions, which add motion or subtract motion to that shared motion between the two ions, or carrier transitions, which don't change the motion at all. And one of these beams is pi polars, another sigma, so we end up driving delta m equals 1 transitions. Another important part of the initialization of our experiment is optical pumping. This is necessary because when the ion is in thermal equilibrium with room temperature, only less than 1% of the population is in any given sublevel at a given time. So if we want to prepare in a given state in a rotational manifold, then we need to try to drive the ion to that state. And we do this by driving, so I'm showing here states within a rotational manifold, and then the same rotational manifold, but with a quantum of shared motion added. So we can drive a sideband transition and then remove the motional excitation through cooling on the calcium ion. And by repeating these steps many times, we can push the molecule towards a given state. And this dissipation means that we can make it a unidirectional process. So we want to be able to read out that we've achieved a state we want. And so what we do is we set our B field, which sets our quantization axis, at a magnitude that gives us unique transitions for each rotational number j. And since our ability to tell that we're in a certain state is reliant on this, we want these to be as high fidelity as possible. And what I'm showing here is a sideband pulse saying that we're in j equals 1. And this was taken on a really nice day when things were behaving. And so you can see we get a really high contrast scan here as we detune our frequency. And we can do this for multiple different rotational levels. We have j equals 1 through 6. And so we can detect if we've made it to the state that we want to be in. When we're performing spectroscopy, we want to make sure that we're not performing spectroscopy of our trap. We're more interested in performing spectroscopy of our molecule. And so we'd like to do operations that don't rely on the motional mode frequencies. So what we can do is prepare in a given state and then attempt to drive a transition that doesn't change the quantum motion. And then we can do our sideband readout on the state that we left or tried to leave and see if we were successful. And so what we can do here, this is showing for j equals 1 and 2, as we scan the detuning of our lasers, we can see that our initial state detection probability is high if we haven't left. And then as we're successful in driving the transition, this drops down and back up again. Down here, I'm showing as we scan the pulse duration while we're centered frequency-wise, we can coherently flop back and forth between these two states. And so this is a coherent process. In addition to performing spectroscopy within a manifold, we can perform rotational spectroscopy. It works pretty much the same way, except that we're driving these terahertz scale transitions with a frequency comb. And so how this works is we have frequency comb split into two beams. We have AOMs to control the detuning between it. And so we can set our frequency spacing so that many pairs of comb teeth can act in concert together to drive the transition we want. So it's effectively many, many pairs of low power Raman lasers, but together they can all act together to drive the transition. And we can effectively drive any transition we want as long as it's within the bandwidth of the frequency comb. And so I'm showing here, we're able to drive a transition from rotational number j equals 2 to j equals 4. And if we set things up in the right way, we can verify the arrival of the molecule in the state we want, which is a nice cross check if you're a little unsure about your assignments. And again, we're able to coherently flop back and forth between two different rotational levels as we were for two states within a rotational manifold. If we do this sort of rotational spectroscopy on a lot of different levels, we can constrain the molecular rotational constants for our calcium hydride molecule. In introductory physics, you probably have seen the rotational energy written just as its first term, but you can talk about a lot of higher order corrections. And we're pleased to see that our rotational constants that we derive are in good agreement with theory. And for the lower order constants, we're able to get quite a bit higher precision, though towards the end, we're just more comparable. So we're very excited with this, but we'd always like to do better. And so in order to improve the resolution of our measurement, we've undertaken some improvements to our frequency comb recently, because previously our interrogation time was limited by the coherence of this comb. We've added a nonlinear fiber to produce a broadband spectrum of comb teeth so we can lock to an optical reference instead of microwave reference. And we're really fortunate to be at NIST, and within our own group, we have a really stable aluminum ion clock laser that we can stabilize to. And we have a new interferometer that allows stabilization of the carrier offset frequency. And I want to make clear that this isn't anything amazing as far as frequency combs go, but it's a really big improvement for us. And we're really grateful to a couple people from the OFM group at NIST who've been helping us out with this. So we've been able to improve our experimental resolution. Before, we could fit our line centers to some tens of hertz. And now we're able to realize 128 millisecond probe times. And that gives us fit uncertainties of less than a hertz. So over here, I'm showing a frequency scan as we're driving a transition from J equals 2 to J equals 4. And we're able to significantly narrow down this frequency scale. And for this particular transition at 2 terahertz, this is a fractional statistical uncertainty of 2.5 times 10 to the minus 13. As I mentioned, I'm going to shift gears just a little bit here and mention that we can use these quantum logic techniques in order to prepare an entangled state between the atomic ion, so the S and D levels in the calcium, with two states we can label as up and down in the molecular ion. And we performed this with a couple of pairs of up and down states. We've done it for 2 states within a J equals 2 manifold that are spaced by 13 kilohertz, and 2 states in different rotational manifolds that are spaced by 855 gigahertz. And I'm not going to go into the details of this, but the contrast of these plots tells you the fidelity of your ability to make this state. And we've been able to achieve 87% fidelity in the within the manifold case and 76% fidelity in the between manifold case. You're not going to want to go out and build a quantum computer with this fidelity, but it is a nice proof of principle that you could use molecules as part of your quantum system to transduce information between different frequencies. I'm going to finish up this talk by talking about a systematic effect that we've been looking into recently, which is that due to the RF electric field experienced by the ion inner trap. So in a perfect world, if you had infinitely long electrodes, you would be able to apply compensation voltages to your DC electrodes in such a way that you could park yourself at the RF null, and the ion would experience no RF electric field at all. However, we do not have a perfect trap, and it wasn't really designed with high symmetry. And so even when we do our best job of compensation, we have at least 850 volts per meter of axial RF electric field at the trap RF drive frequency of 86 megahertz. And other traps have been designed with higher symmetry and can have a much lower electric field on the order of 50 volts per meter. And maybe someday we'll switch over to something like that, but for now, this is what we have. And what we can do is turn into a bit of a tool for us. We can adjust our DC electrodes, the bias between the DC electrodes, and use voltage applied to this DC mask in order to push the ion around and sample different RF electric field magnitudes and polarizations. And what we find is this RF electric field at the trap drive frequency can cause Raman type coupling via nearby rotational states. And when I say nearby, I still mean very far away. So our RF photons are at 86 megahertz. Our different rotational levels are at hundreds of gigahertz or terahertz away, and states within a manifold are at 10 kilohertz spacing or so. But we can see that these RF photons do mix states and can cause shifts. And the electric field polarization determines how different states are coupled. So if you have mostly sigma polarization, you can couple delta M equals 2. And if you have sigma and pi, you can couple delta M equals 1. We also see that this causes shifts between rotational manifolds. And this can be a little bit complicated to write down, but the shift of the J equals 0 manifold in particular has a fairly simple form, which we can write down as the frequency shift is proportional to the R electric field squared times the dipole moment of the molecule squared over the rotational constant. And as I've shown you earlier, we spent a lot of time measuring the rotational constant pretty carefully. And so we could see that if we were to do some frequency measurements and measure and vary the R electric field, we can get some information on the dipole moment of the molecule. We can also see that this shifts, the systematic effects will be smaller or bigger, depending on how you want to see it. If you change the R electric field seen by the ion, if you use molecules with differently sized dipole moments, for example, a homonuclear molecule won't have an electric dipole moment and so won't be affected by this to first order. Or molecules with large rotational constants will have a smaller effect. So we performed this experiment. We put our ion in different places in our trap so that it sampled different RF electric fields and measured some J equals 0 to 2 transition frequencies. We started in a state in J equals 2 that's relatively unshifted by this. And we're able to measure this RF electric field using cytobanded carrier pi times on calcium's quadrupole transition. I've plotted here the electric field squared so that we expect a line. And if we do some parametric bootstrapping, we can get some good information about our intercept uncertainty and our uncertainty in the slope. We find that the intercept uncertainty we can get down to plus or minus 50 hertz or so for this transition. And this is the field free value of the transition frequency. That's what we really want to know when we're doing spectroscopy. We want it to be a number that can be compared to molecules out in space or something on your trap. The slope with some scaling gives us the dipole moment of the molecule, and we get a 95% confidence interval that looks like this. And this is in agreement with theory, which is great. And I do want to point out that we are still narrowing down our error budget a little bit here. So this is preliminary, but we are working on writing it up. Looking to the future, we have an ongoing, or we're beginning to set up a cryogenic experiment in our group. Cryogenics will really help us in a lot of ways. I haven't mentioned this, but the lifetime of a given rotational state in our molecule is limited due to black body radiation and rethermalizing. We'll also have a lower background gas collision rate. And we're planning to put in a trap that will have a lower axial RF electric field. So the systematic I've been talking about for the last couple of minutes won't be as big of an issue. And we're also looking to try out other molecular ion species. So in conclusion, I've talked with you about quantum logic spectroscopy, and I hope I've convinced you that allows for interrogation of an otherwise difficult to probe molecular ion. After the heralded transition, we know the pure quantum state of the molecular ion. All of our laser molecule interactions are with very far detuned light, which allows us a lot of flexibility in choosing different molecular ions to study. And so with that, thank you all for listening. And thanks so much to the people in the ion storage group. This is a pre-COVID picture, obviously. And the people that work directly on this project. Dee Dee, Dave, and James are staff members who work on this. Julian and Dalton are heading up the cryo system. And we've got a couple of former members listed here too, as well as the OFM group who helped us with our frequency comb and our theory collaborators.
Thank you very much, Alejandra, for a really interesting talk. Appreciate it. All right, there's still time for others to enter questions into the Q&A. We have a few here, and I'll begin. The first question is from Wes Campbell. Says he's enjoying a very nice talk. If the ML laser, I guess that means the mode lock laser, is driving stimulated Raman transitions, why do you need to stabilize the carrier envelope offset phase? I would have expected that to drop out.
So it does, in the sense, we used to not stabilize that at all, and it worked just fine. But we're able to get better coherence out of the laser if we have both stabilized.
Very good. All right. The next question is from Dima Butker. Congratulations on very nice results. Could you kindly explain how you load a molecular ion into the trap?
Oh, sure, thanks. I totally forgot to mention that. So what we first do is we load 2 calcium ions just with a calcium oven. We have some photoionization lasers so we can ionize them in the center of the trap. And we have cooling lasers so they get trapped pretty well. And then we do a kind of hacky thing, depending on how clean you like your ion vacuum chamber to be. We just leak in some hydrogen gas while cranking up our main cooling transition. Because we can only make the hydride when we're in the excited state, we want to rapidly cycle. And then after some number of collisions, we make a hydride. And then of course we stop leaking in hydrogen so that we don't have too many more collisions.
Very good. And then we have a few questions from the panelists. Well, I have a question. How do you decide which molecular ion or which ion to use as your logic ion? Why did you choose that particular other species?
So for calcium and calcium hydride, it's a little bit of a matter of convenience. You do want your mass of your 2 ions to be relatively similar so you get better cooling. But calcium hydride is also the molecule you accidentally make when you're trapping calcium. And so it's a little bit of a proof of principle molecule for us. It's a relatively simple one to understand and model, and is easy to produce. But in the future, we are excited to look into other molecules. I think the big thing you want to look at is really the mass ratio.
Right. Well, maybe I'm going to skip. There's this related question then from Shimon who wanted to know, can you do this with larger, more complicated polyatomic molecular ions? What would be the requirements on the logic ion mass? And are there ways to get around the difficulties in the initial molecular state initialization?
Yeah, so there's a couple of questions there.
Yeah,
so the rule of thumb is that you want to be within a factor of 3 mass-wise. And so if you had a really heavy logic ion, you could still imagine having a reasonably sized molecule. But as far as state preparation goes, it does get much more complicated, and it does get more confusing knowing, like, am I driving a unique transition in the molecule, or is it kind of a crowded forest? And so I think that's something we're going to try to step up into gradually. We are looking to get more deterministic in our state preparation, but it does take some knowledge of the molecular state so you can choose the pumping that you're doing and so on.
Very good. All right. Maybe one last question here. One from Adam asks, do you have to worry at all about beating between different Raman-Rabi frequencies achieved by different comb teeth pairs? Or is it fairly straightforward to keep those frequencies similar?
I'm not 100% sure I understand what you're asking. So the comb teeth spacing we lock and stabilize. And so many different comb teeth are driving the transition, but they're not shifting around with respect to each other, if that makes sense.
Right. All right, maybe one last question. Do you think about this, or these kinds of ion traps thought about in the context for quantum information processing, whether it be for sensing or something else? Are there some advantages of ions versus atoms?
For quantum information, I'd argue there's definitely different schools of thought on this, but I think ions are a really promising platform. All of your qubits are the same, which is a really nice place to start from. As far as particulars of ion traps, a lot of the quantum information stuff is happening more in surface traps than these like large 3D traps, because they're more likely to be scalable.
Right. Very good. All right. Well, let's thank Alejandra again for a wonderful talk, and Zach, and we really appreciate having these postdoc double headers, and learning about what's going on at the grassroots. So thank you for sharing your research with us. Let's see, in the chat, we arrived now the post-seminar discussion. Particularly welcome everybody and students who didn't have opportunities to ask their questions. Also, we are, as the board, always waiting for your recommendations and nominations for future talks. So please remember to do that. And we'll see everybody after a very safe Thanksgiving. So be well.
Just a reminder that our next talk is December 4th, not next Friday.
Right. So that was kind of what I meant. We won't be here for Thanksgiving. We'll be safe in our homes, but then we'll be back with you the week afterwards. All right. See you at the post-seminar.